So thanks for the introduction. I think that takes. Oh, is this gonna work? Oh yeah, it is. That takes the wind from my first slide actually, since you said everything. Yeah, I was born in Czech. I did my master's in Denmark with the topic mechanical ventilation in cold climates. That was my first experience with cold climate when I went to Greenland and did measurements there. I fell in love so much that I applied for a PhD, which was also placed in Greenland for most of the time. And the topic was energy use and indoor air quality in cold climates. And within that PhD, I was fortunate enough to meet Jack and come here and do all this interesting work. When I finished, I actually moved to Greenland, so that's where I live right now. And I'm employed at the Center for Arctic Technology up there, which is something a little similar to what we are in right now, but it's much smaller scale. And my topic is, or my subject is heating and ventilation systems in cold climate. So you know me now, but I don't know almost any of you actually. So I would just like to do a little survey to see who is here. I've heard there might be some homeowners or some builders. So maybe raise your hands who is a builder. 1, 2, okay, homeowners. All right, cool. And the rest? Just interested or just
architect
or architects?
Engineers.
Okay, engineers. Okay, perfect. So I hope each of you will find something, at least part of this presentation, interesting. And please ask on the go. And if you have any questions, we go through them as they pop up. We're going to start with a little introduction to indoor air quality and health. Then we talk about how actually bad or good is indoor air quality in cold climates. Then we'll talk about ventilation systems. Then we'll talk about a project I'm working on right now in Greenland, and it's a renovation of a house for better indoor air quality. And then we go for a tour where I take you through some of the ventilation units here in the house, and we can talk about different systems and your questions if you have any. I hope you will. So when we talk about indoor air quality, what do you think could affect indoor air quality? Do you have any substances or any ideas of what could make indoor air quality good or bad?
Odors.
Odors, right?
Products used in building the house.
Construction.
Yeah.
Outside air.
Outside air, yeah, especially here in Alaska when there are fires and or especially fires.
Good or bad?
Cooking.
Cooking, right?
Pets.
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 Oh, pets. Pets, okay. How about ourselves? That partially is odors, right? Like,
Respiration.
yeah.
Combustion.
Yeah, combustion, right?
Moisture.
Moisture. How about stuff we use in our household to clean and to
Chemicals.
chemicals like probably VOCs, right? All right, I think we've got plenty. There are some mores in here, like tobacco smoke, for example, dust mites. candlelight actually. It's a big issue in Denmark or Greenland where there's a huge tradition in burning candles inside. Carbon monoxide, carbon dioxide. So we're going to take them one by one and fly through them. Moisture is not really an air pollutant, but moisture helps some of the other pollutants to spread, and it enhances growth of different things like bacteria, viruses, fungi, mites, and other stuff. And it's tricky with moisture because if it's too low, it causes discomfort. If it's too high, it causes problems as well. So ideally, we should stay within some range when it's optimal to eliminate the growth of bad things and to enhance our own growth. So something between 30 and 50% is typically recommended. When we talk about moisture, there is two things. There is relative humidity and there is moisture content. And there is a relation between them, and it's especially important here in Alaska when it's so cold. I don't know how many of you are familiar with this chart, but just briefly, this chart shows a relation between relative humidity and moisture content in the air and the temperature of the air. And we can see here on the horizontal axis there is an absolute moisture. That means how many pounds of water there is in every pound of air. Then there is a vertical chart, and that's temperature. And then these curves, those are relative humidity. So what we can see basically is that if we have air which is, I'm sorry these are in Celsius, but yeah, let's see. If we have air which is 23 Fahrenheit, and it has 0.0025 pounds of water in it. It's fully saturated. That means that there cannot be any more moisture in it. That means that it's 100% relative humidity because it has as much moisture as it can have. But if we take this air and heat it up to say 68 Fahrenheit, its capability to contain moisture enlarges very much. But there is no moisture in it anymore, so the relative humidity drops to 20%. And that's what's happening here in the wintertime. It's so cold outside that the air cannot contain any moisture, but when we open windows or go out and in and bring that air inside, it gets heated up, and so that's why it's so dry. Then we of course produce some moisture by breathing, cooking, drying clothes. So the humidity and perhaps also the temperature of the air rises a little bit, and we get somewhere here. That means we are still around 68 Fahrenheit, or let's say 70 Fahrenheit now, and we have a comfortable 50 or 60% relative humidity. But now when this air gets in touch with a cold surface, it starts cooling down, and it goes this way. You can see that the relative humidity is rising, and eventually we get here, that is 100% relative humidity, that's a dew point. And that's, in this particular case, it's 57 Fahrenheit. So what we can read from this chart is that our air, which was 70 Fahrenheit and had 60% humidity, when it gets in touch with 57 Fahrenheit surface, it starts forming fog, or it starts condensing on it. We're going to talk about this a little bit later as well when we get to the ventilation systems and to the problems this particular thing causes. But moisture, if it's too high, it enhances mold growth. Mold feeds on dead organic matter like wood, chips, cellulose, and it can live off many materials found at our homes. So gypsum boards, for example, or wood chip boards, plywood, even solid wood. And the higher is the water activity or relative humidity, that's the same, the better it grows. And there are species of mold which are not harmful to people. Some are even beneficial, like penicillium, we all know that. But there are species which actually are harmful and can cause serious problems. Unfortunately, so are the cleaning agents, because most of them are based on chlorine, and breathing chlorine is about the same bad as being in touch with the mold itself. So we definitely don't want too much mold, or we don't want any of the bad mold in our house. Dust mites, most of you probably know these little creatures. They live of skin flakes or of skin remains, and therefore they mostly prevail in living in bedrooms, in mattresses, in carpets, in teddy bears, everything which is fluffy and which our kids touch and which we touch. That's a good environment for mites. And also, the higher is the relative humidity, the better is the growth of mites. And speaking of mites, we know that they are associated with asthma and allergy, especially in kids. There come our VOCs, which stands for volatile organic compounds, and those are chemicals that can vaporize when the temperature is not that high. Actually, even at room temperature, as we are now, some chemicals could vaporize and stay in the air, and they can be really harmful if at the high concentrations. They are typically from paints, waxes, cleaning agents, and some of them are listed here, the most deadly ones or harmful ones. And they are known for childhood leukemia, retarded growth, birth defects, or even human carcinogens. Environmental tobacco smoke, also known as a secondhand smoke, that's actually even worse thing than the smoke itself for the smokers, because it is often exposing kids, and it causes asthma and irritation of the mucous membranes, something called sudden infant death symptom that has been linked to environmental tobacco smoke. It may also cause miscarriage. It is a group A carcinogen, and there is over 3,000 deaths a year around the world which are linked directly to secondhand smoke through the lung cancer. Candlelight, especially candles made of paraffin, they emit toluene and benzene, which are volatile organic compounds, harmful to people. They cause allergies, asthma, cancer as well. It's definitely better to use beeswax if somebody needs to use candles at home. But it's still, even the beeswax or soy-based candles, they will still produce carbon monoxide, and they will still soot if burning improperly. It's important to be aware that not always a candle made of beeswax is 100% beeswax. Many of the producers, they label their product as a beeswax, but to lower the cost of production, they would still use certain percentage of paraffin, which would then cause the problems again. Carbon monoxide, that is a leading cause of poisoning deaths in a world. Just in the US, it's about 430 deaths a year due to carbon monoxide poisoning. And those are not deaths in house fires. Those are just purely deaths in a poisoning. It's odorless and colorless, so that makes it tricky to find. And in low concentrations, it causes fatigue and chest pain. And if the concentration is higher, but not high enough to kill us, it would cause flu-like symptoms and headaches as well. Carbon monoxide indoors, it is a combustion product as well as carbon monoxide, but it's also a product of fermentation and the respiration of living creatures, human, pets, animals. In the outside air, there is about 400 ppm, particles per million, or 0.04% of carbon dioxide. And we know that carbon dioxide is linked to affect human performance and how we perceive the indoor air quality. However, with the it is also known that with rising CO2 levels indoors, it's also other pollutants which concentration will rise as a result of poor ventilation. So some of the effects of CO2 have been mistakenly linked to CO2, whereas it was actually other pollutants causing it. Anyways, the CO2 concentration is used as an IAQ or indoor air quality indicator because it follows the concentration of other chemicals typically. And there's been some regulations or some recommendations for CO2 concentration inside. The ASHRAE here in the US says 700 ppm above outdoor concentration. So if we say that it's about 400 ppm outside, we should have about 1100 ppm inside. The ASTM standard says 650, European standard says actually several levels, but the one similar to ASHRAE is 500. And very commonly, we just take 1000 ppm. Because, I mean, give or take 50 ppm, that's not such a big difference. And we say that 1000 ppm is a good level to be maintained inside. Now it's a good time I introduce you my little friend in here. That's the indoor climate monitor, and those of you who can see the LEDs here, we are now at 980 ppm. So we are still good, you are still up, and you can concentrate, and we can go on for another couple hundred slides. How does the CO2 look in a typical bedroom which is not mechanically ventilated? That shows us this chart. This is over the course of 2 days, CO2 concentration measured in a bedroom. And we can see that, of course, 9 o'clock in the morning, it goes down, and then whole day it is way below 1000 because there's nobody there, so there's no production of CO2, so even a little air change would be enough to maintain such a low level. But then, 8 o'clock, before 9 o'clock in the afternoon, somebody probably goes to bed, and then the concentration starts rising and rising and rising and goes way beyond 1000 ppm. And then again, 7 in the morning, when the person leaves, of course, the concentration drops down. So in this particular bedroom, we can see that the night concentrations have been over 2,500 here and close to 3,500 in the second night. So it doesn't kill the person, that the concentrations are too low to actually do real harm, but it affects the quality of the sleep for sure, and it may cause a morning headache or tiredness after the long night sleep. So the known effects of poor indoor air quality have been the quality of sleep can be affected, concentration and performance. The higher is the CO2, especially in schools or office environment. It's been found that the concentration of CO2 has an effect on a concentration and productivity actually of the employees. It may cause a sick building syndrome. It may cause asthma or worsen the asthmatic symptoms, allergies, irritate our mucous membranes. In a worst case, it may cause cancer or some of the substances in a poor indoor environment, or poisoning. So what is the solution to poor indoor air quality? We need to get some fresh air in and get that polluted and stale air outside. And how do we do that? We're going to get to that in a minute. There are some requirements for ventilation. There is a health-based minimum that is 8 cubic feet per minute per person. That is the absolute minimum a person needs to thrive. However, there are European or American requirements, which both of them basically say the same, just in a different way, that there should be about 15 cubic feet per minute per every person. Then there is Alaskan environment requirement, which is a little more strict than the American one, and we will see that best on the example right here. And if we have a house which is about 2,000 square feet has 3 bedrooms and 4 people living in it. Formula, we get about 50 cubic feet per minute, which is 12.5 per person. And if we use the actual bees, then we get 10 cubic feet per minute more, and that's the 15 CFM required by European standards as well. So we know what we should do, but what do we really do? And now I'm going to talk a little bit about what the Greenlanders do. A little introduction to Greenland to begin with. There's about 65,000 people, or 55,000 people living in that island. They live in 23,000 dwellings, which about half of them is apartments. 1/3 of all the dwellings was built before 1970, and they are in mostly in very poor technical and environmental conditions because they haven't been maintained and they haven't even been built properly. There is extreme climate in Greenland, which is very similar to Alaskan climate, although Fairbanks is way different in a way that there are much higher extremes. There still was a snow 3 weeks back when I left Sisimiut, so the winters are much longer, but they are not that cold. So are the summers. The summers are short and cool, whereas here it's much more extreme. On the other hand, the amount of heating degree days, for example, is the same. So in that way, it is similar. The average energy consumption in those dwellings is about 14 million BTUs per square feet a year. Excuse me if I used completely wrong units because I'm used to metrics. So if you use something different, you have to convert that yourself. There has been lots of intentions to save some of that huge energy amount, and one way to do that is that people just seal their buildings and they eliminate the air change to have less energy consumption, which together with long-lasting cooking, which is a big tradition in the nation, and of course drying their clothes inside, that creates a lot of problems.
What is long-lasting cooking? So like crock pot, stews?
Boiling.
Seal, like boiling for a couple hours, which generates lots of moisture and odors.
Rice cookers? That would be here.
Yeah. So what I did during my PhD was a study of indoor air quality in the town of Sisimiut, where I actually happen to live now. And that town has 2,000 homes, and out of these I selected 80 where I did measurements of temperature, humidity, and CO2, 1 week in the summer, 1 week in the winter. What I found was that people very often, well, that was not that surprising, people very often complain about cold draft in their homes, about having cold floors. What was surprising though was too high temperatures in the summer, because it's not that hot in Greenland. You barely get temperatures over 60s. Still, there is so much solar gains that the buildings get overheated because there is not enough ventilation or not enough cold air from outside. Too cold in the winter time, that was not that surprising. And lots of people complain about condensation on their windows, which is a marker of that something is going on or that something is wrong with the indoor environment. Lots of people smoke inside. About 30% mentioned that they smoke inside, and it didn't make statistical difference whether they have kids home or not. So that was actually striking a little bit, that no matter if there are little kids, people will still smoke. Another thing was that bedrooms with kids had poorer indoor environment. We couldn't find why could that be. Probably that parents don't, or the kids themselves don't want to open their window even for a minute a day, or that some kids of course sleep with their adults, so that makes more CO2 generation. But still, the younger, the worse. Unfortunately, also the newer, the worse, because the newer are the buildings, the more tight they are. They put vapor barriers. They try to do all right as they should, but they forget that single little last thing, and that's the ventilation. So they still use the fresh air inlets, which are commonly used here as well, and they just don't work. So here on this chart, one can see the CO2 concentration as it goes over the night course. So in average, 50% of the time, the concentration in the newest dwellings in the winter time, that is the red curve, was above some 1200 ppm. We go 2000 ppm, still we have about 25% of the night time, the concentration was over 2000 ppm. Here the older buildings, because there are more cracks and leaks, so there still is at least some air change, they are doing still rather poor, but better than the new ones. So no matter what the requirements say, we still build buildings with poor indoor air quality. And that's what studies all over basically all over the world show as well. I mean, it's when you look at the studies here done here in Alaska or in Canada, northern Finland or Sweden, they both they all come with a similar conclusion. So there is time to do something with that, and one of the experiments or one of the approaches is to build demonstration projects, and that's what happened here some 2-3 years ago with the sustainable village. I suppose you are familiar with it. And it was finished by the time I was here, so I was lucky enough to do some measurements in that village as well. It was built 3 years ago. It's 4 homes, each for 4 students, and each of them has a slightly different solution. There are different foundation types, envelope types, different heating systems, and slightly different ventilation systems. But the principle in all 4 of them is build tight and ventilate right. So it was interesting to see how different approaches affect the indoor air quality. And what I was able to measure was the airflow in each of the homes, and how the CO2 concentration relates to that airflow. And clearly there is a link between the amount of fresh air delivered to the house and the CO2 concentration as an indoor air quality marker in the home. So the house with the highest amount of fresh air, actually close to what it should have, if we have 4 people living there, was only slightly above 20% of the night time. The CO2 concentration was higher than required. And then, of course, the house with the least ventilation had the highest CO2 concentration. I will get back to this figure a little bit later today. And we should talk about what the indoor air quality is in this room. It's not that bad, actually. I was expecting that it's going to be much worse.
Jack opened some windows. So we can play there.
Good one, Jack.
Okay.
It did drop. I watched it go up and then come back down.
You spoiled my moment, Jack.
Sorry, buddy, that's what I do.
Never mind. The thing is, I was going to show you how this room is ventilated, and I intentionally turned that ventilation off before you came, and I was hoping that it's going to rise much more.
I can close them again, Michael.
Yeah, let's give it a try. Yeah. But anyways, when this addition was built, also 2 years ago, I got a chance to propose a design for the ventilation system, and we're gonna walk through it, so you're gonna see it, and we can talk about it as we go. But just for this particular room, you can see that there is gonna be a partition soon, so it can be divided into 2 classrooms. And when I took the requirements for the ventilation, They require enormous amount of air, no matter if people are here or not, because unless you have a demand control ventilation, you have to ventilate all the time. So then we thought, well, let's do the demand control ventilation because we have to save lots of energy heating all that air. So and that's what we did. So there is a main branch of the fresh air coming from over there, and then it branches here into two small branches, and one goes to the back of the room, those 4 inlets over there, and the other one goes to these 4 inlets in here. And then the same with the exhaust, and then we have 2 CO2 sensors which are now plugged off, and once one of them senses elevated CO2 concentration, it would open the dampers on that particular branch to one half or the other half, and that will send a signal to the ventilation unit, and it will boost up the ventilation. So right now, since the sensors are off, there is no ventilation in this room. The moment I plug them in and the CO2 concentration rises above certain level, it will start ventilating that part of the room. And it's 2 parts because if the partition is on, we can split into 2. And question is if we need a break or not.
To raise the CO2 level.
Yeah, so maybe we should do a little exercise.
A couple of laps.
Burpees.
If you need some water or coffee, we've got everything. So
One light, one dark.
If you want to have a cigarette, go ahead and experiment. How that works out.
CO2 that messes with the CO count.
What's the CO2 at, Martin?
it's at 960, 970 right now.
Okay, no, it was in the yellow before it got.
Okay, so how do we ventilate? There are basically 2 principles. Either we do it naturally or we do it mechanically. If we do it naturally, that means passively without electric elements and ventilators. We use a stag effect or a wind pressure to drive the air through the house. That means that the air comes through the opening underneath the window or somewhere low, then it gets heated in the house, and then it leaves the house close to the roof. It's a very difficult to do heat recovery in this principle, because heat recovery usually introduces a lot of pressure loss, and the natural airflow is not able to overcome that. There is very limited controllability. There is very poor energy efficiency because we need to heat all that cold air which comes from outside. We need to heat it up to a room temperature in order to feel comfortable. But that very often results in a poor air change because nobody wants that cold air to come in, or that causes lots of discomfort in occupants. And it has proved not to work in Arctic climate. Because once we install these fresh air inlets, people will always find their way how to block them, seal them, tape them, or just avoid any cold draft in their home. So the other option is mechanical, which is active. It uses ventilators to move the air around in the house, out of the house. It's good because it gets much better controllability. We can regulate the speed of the fan. We can turn it on and off if we need. It can be used for air heating or air cooling in the summer. A huge advantage of that is that we can use heat recovery to get some of that heat which goes out with the stale air, to get some of that heat back. We can use air filtration or purification. That is really important if we have a sick person in the house, or if we have some issues with the outdoor environment, like lots of ash or dust. So we can actually make the indoor environment even better than the outdoor. A huge drawback is that it requires maintenance. It always does. It always did. And it always will. and it's a higher investment, but we'll talk about the economy in a few slides as well. So when we talk about mechanical ventilation, it's real hard. It's a ventilation unit. It's a small box. Most of you have probably seen them. There is a filters in that in the entering terminals. There is a heat recovery core, and we have two kinds of ventilation units. We call them HRVs or ERVs, depending on what kind of energy they recover or what kind of heat they can recover. The HRVs, they only recover sensible heat. That means they only transfer the heat from the outside air to the incoming air without any moisture transfer. On the other hand, the ERVs, standing for energy recovery ventilators, they can also recover some of the moisture, because the air going outside of the house is moist, and the one coming in, especially in the winter, is very dry. So it might be beneficial in some periods of the year to get some of that moisture from the exhaust air to the supply air. And heart of the ventilation unit is a heat recovery core, and there are, I would say, two principles or several principles how that could be made. The most common here in Alaska or perhaps in US is the flat plate heat exchanger, and that's nothing else than just a set of membranes or plates, where in every even plate there is the exhaust air, and in every odd plate there is the fresh air. And as they pass through the plates, they exchange the heat. If the material is made of a membrane, if it's a membrane material like a Gore-Tex, for example, then the moisture could also travel through the membrane or through the wall, and that's how the moisture recovery is done. There basically are two different kinds. One is cross flow, that's where the flow goes perpendicular to each other, and one is counterflow, where there is a section, at least a small section in that heat exchanger, where the airflows go opposite to each other. That's usually much higher efficiency when it's done like this. They also take more space than the cross flow. The other type of heat exchangers, and we're going to see that today as well, is a rotary heat exchanger. They haven't gained a very good name in cold climates in the past, but they are coming back as the development have evolved a lot. And the principle of this heat exchanger is that there is a rotor which is made of a honeycomb channels, and that rotor is slowly turning around, and then it sits in the unit, and there is two chambers horizontally divided. The bottom one is for fresh air, where the fresh air goes this way, and then the upper one goes where the stale air goes. So the stale air preheats the chambers here, and then they rotate to the fresh air when it takes the heat from that. This one actually could also be, the chambers could be painted with a desiccant, so they have a very good moisture recovery, because the moisture on the stale air gets absorbed in the walls, and then when it gets to the fresh air, then the moisture evaporates back to the supply air. Or even if there is no desiccant on the walls or on the material, there still is a certain moisture recovery, because if there is a condensation, the water drops will stay in the chambers and then evaporate as they get down. And then the third type, that's a coil heat exchanger. That is not used in small units that much. It could be used in large applications because of its complication. It's complicated, and because it requires a pump to circulate glycol from the cold heat exchanger, or from the cold coil to the warm coil. The advantage of this one is that we can regulate the speed of the pump and that way regulate the efficiency. So, as we're going to talk later about, the freezing problem can be avoided by this. And the same applies for the rotor, because we can change or we can vary the speed of the rotor, and that way we can regulate the efficiency of the heat exchange. Yeah, a little bit of math. When we talk about heat exchangers or heat recovery units, we always are interested in effectiveness. And effectiveness is just the amount of heat which is transferred actually over the amount of heat, over the maximum amount of heat which could be transferred. And these all things go to very simple formula as long as the mass flow of the air is identical on supply and exhaust side. So if we have the same speed of the fan and the same airflow back in and out of the house, we can just use this simplified temperature formula to find out how warm or how cold will be our supply or exhaust air after it passes the heat exchanger. And there is a little example to it, which assuming that we have a 70% efficiency or effectiveness of the heat exchanger, and we have an inside temperature of 70 degrees Fahrenheit, that is our return temperature, that's the air what goes out. And then we have an outside temperature of minus 40, then we can calculate how cold will be the air which goes out of the house after it was cooled down. And then we just calculate, do the math, and we end up with minus 7 Fahrenheit. That's quite a cold air. And what does that mean? If that air from inside of the house should be cold to that temperature, there is a lot of moisture in that air. And we are back to our Molière chart. If we have a 70 degrees air and suddenly it starts cooling down on the heat exchanger, it hits the dew point, which is still above freezing, so that's relatively okay. That's where the condensation starts inside the heat exchanger. But then suddenly we reach the freezing region, and now all the condensation is basically a frost formation. It doesn't condensate anymore. It directly transforms to ice layer in the heat exchanger. So we actually never get to that minus 7 Fahrenheit because we have to protect that heat exchanger against this to happen, because if we don't, then eventually the whole heat exchanger will turn into this.
Mm-hmm.
And this is actually not that bad. There is still some passages where there is space for the air to go, but if this was going on for long enough, then the whole or half of that heat exchanger, which is on the exhaust stream, would be filled with ice. And then we just have to stop it, open it, and wait for a couple of days until it melts. So how do we deal with the freezing? There are several strategies which are used in the ventilation units nowadays. The most simple one, and probably the least effective one, is preheating. We can just have a simple electric element on the cold stream and have a controller set that if the outside temperature drops below something, just turn that electric element on and preheat the air. It is efficient to protect the heat core, the core from ice formation, but also it reduces the efficiency as the temperature difference is lower. What we could do though is, instead of electric, use a ground loop, and that could be used here in Alaska as well. If you build your house, you can either underneath the house or around bury a loop which will be filled with glycol and a small pump, and then have a coil which will preheat the cold air outside, the cold outside air. Another opportunity or another strategy is bypassing. That is basically a certain amount of fresh air will be sent around the core, so there is more warm air going through the heat exchanger than the cold air, and therefore there eventually will be melting in the heat exchanger. Of course, the ratio will vary according to the outside temperature. So eventually if the outside temperature is too low, you might actually get 100% of the air, of the fresh air going bypass to the room, and only the warm air going through the heat exchanger, trying to melt all the ice. Having this strategy, you should have a heater here, which then after heats the air before it goes to the room, because otherwise you could get 40 below air blown into your room. Little similar strategy would be flow reduction. That is, some units can reduce the speed of the supply fan, so you have until it eventually stops again. So you again have just the warm air passing the heat exchanger, and then the whole house is under pressured, and the fresh air comes through the leaks. The problem with this is if you have a new house which is tight, then the air comes through small cracks or tiny little holes, and it can make noise, or actually in the best way, it will not come. I mean, there will not be enough cracks or leaks for that fresh air to enter the space. So every time you open the door, you would feel a resistance because of that under pressure, and it's a good strategy for a short term, maybe in old homes, but in a very new home, I would recommend that one. Unless you have a special opening for that fresh air. I mean, you could have a hole which opens when that happens. Another strategy is recirculation. That is a strategy very common here in Alaska. In most of the units which are sold here, they have this one, and that basically is that if the temperature outside drops below a certain level, then the unit rearranges some dampers, so it basically closes to the outdoor environment, and it's just circulating the inside air. So we can see it here in the picture. Under normal operation, the return air from the house goes to the unit, then it goes through a heat exchanger and goes out of the house. The fresh air comes in, it gets preheated, and it goes to the house. When the recirculation is active, then the return air comes to the unit, goes through the heat recovery, gets cooled down because it's heating the heat recovery with all the ice in, so it cools down a little bit, and then through this hole goes back to the house.
So how does that help your IQ situation?
That is what I'm going to talk in 2 slides. It doesn't help.
Helps to keep the core from freezing.
That's right.
It doesn't improve the air quality.
That is right.
It's a temporary measure.
It is temporary measure, only the problem is that if it's 40 below, it's a permanent measure. So, but I'm going to show you a picture of how that works in practice. Another way how to protect from frost protection, how to protect from frost is regulation of effectiveness, and that's these 2 heat exchangers can do that. You can either stop the core, or you can slow it down so there's not so much heat exchange, and or you can regulate the speed of the pump. Or actually in this system you could have a little heater here, so that would even heat the glycol to melt the ice formation if there is any. When it comes to controls of the ventilation units, there can be simple ways to control them or some advanced ways to control them. Of course, the cheapest units usually are only equipped with a simple controller. That means we can only regulate in a few steps the speed of the fan. We cannot decide whether it's defrosting or not. It's either defrosting or not, so when the temperature drops below a certain level, it just goes on defrost. Also, if some of them have heating coils, that would just go on and off. On the other hand, the advanced controllers, they would, even on these small domestic unit, units, they would already have some features which are common in the large HRVs or in the large industrial ventilation units, such as variable air volumes or demand control ventilation. That is what we have here. So we can hook up a CO2 sensor to the unit, and if the CO2 concentration goes up, the unit will speed up the fans to ventilate more. They could also modulate the defrosting function, so if it's 20 below, it will maybe speed up or slow down the exhaust fan a little bit. If it's 40 below, it will slow it down even more. Some of them could even be connected to a central control system, which is very useful nowadays, because many of the homes which are built have these smart home automation systems which could easily talk to the ventilation unit then and say, oh, I want to ventilate this room, I want to ventilate that room, or I do not want to ventilate because the people are gone for a week of vacation and so on. And all these things in the end mean more savings, because you only, especially when it's so cold outside, you only want to ventilate as little as possible to feel comfortable, but not to use too much heat for all that fresh air which comes in. Some of them even offer GSM communication, so you can turn them on and off remotely as you go home from vacation and so on. So why is it saving energy? Well, because of the heat recovery, and there is a little example again on the Fairbanks situation. I took 9 months from September to May with the average temperature of 8.4 degrees Fahrenheit, indoor temperature 70 degrees, and I took that house we had on the very first example, so we'll have 60 cubic feet per minute of ventilation air. The heat capacity of the air we have here. So if we for some reason decide to ventilate that home without ventilation unit, just opening the windows as much as is needed to maintain 60 cubic feet per minute ventilation, we would need about 26 million BTUs in those 9 months. That converted into oil and money is about $780 for that 9-month period, if all that air should come in through windows and be heated with our heating system. However, if we have a ventilation unit with, say, 70% effectiveness, then we could cut that down to about $231. We still will have to heat the rest 30% of the heat we will have to deliver with our heating system. So in those 9 months we would save about $500 with an investment into a small house around $6,000. I mean, it depends, of course, a lot on the design, on the layout, and so on. The running costs can be almost neglected because the nowadays or the new ventilation units, they have very efficient motors. So that gives us a rough return on investment about 11 years. But it's not just the return on investment. We're not making investment. We're improving our indoor. Excuse me. You see, the red light goes on. We probably have to wait a little bit more with the ventilation before it kicks in. So yeah, it's a question of health and comfort, not just of the investment itself. So let's look a little bit in the units which are available on the Alaskan market. The most common ones, Life Breath and Venmar, made in Canada, they are very commonly used here. They are simple, that's good and bad. Good in a way that they don't break down so easily. Bad in a way that sometimes they are a bit too simple. They are at lower costs, they have a simple controllers, and they use the recirculation as a defrosting strategy. What that means, you remember that picture from a sustainable village when we measured the airflow, these 3 houses which actually have a Venmar unit, they actually had over 60 cubic feet per minute. But due to the recirculation as a defrosting, the average air change or the average airflow reduced as much as 67% in this case, and as little as 27% in that house. So that answers your question. What does the recirculation do to the indoor air quality? It affects it a lot in a bad way. The good thing about one of the units was that it's got a ERV core, so it allowed for moisture reduction, for moisture transfer. We could clearly see that, yeah, the more fresh air we bring in, the drier will be the indoor environment. So that's not surprising in these three cases, except for this one, which actually has more fresh air coming in, but the relative humidity is somewhat higher because of the moisture recovery in the unit. There comes the German unit, Zender, that also has been used here a couple times, at least I have seen. It has a counterflow heat exchanger. It has electric preheating. It also has a bypass, and it also has a flow reduction. So when you install it, you can give priority to different strategies, and you can decide, to some degree, you can decide what strategy it will use as the fitted preheating coil, which can be hooked up to a ground loop or to any other hot water source. So if you have a boiler which heats water, you can hook it up to that. You can, instead of electric preheating, you can just preheat with hot water.
Martin,
Yeah.
can I ask a question about?
Yeah, sure.
So it seems like in the last few slides, you pointed out that using the bypass is a bad idea and shouldn't be done. Am I overstating that? To thaw the unit out in the other houses in the.
No, I mean, the problem is with the bypass that the air has to come from somewhere. So it's not a bad idea to use the bypass, but you have to think, especially in a new house, if it's tight, you have to make up for that fresh air.
So if you don't make up for that, then you're going to reduce the indoor air quality
Yeah.
by using the bypass.
No, I'm sorry. I the flow reduction would do that. For flow reduction, you have to make up for the air. If you have a bypass, it's all right because you have the same amount of fresh air coming in. It just doesn't get preheated in a heat recovery.
Do you mean bypass or recirculation?
Well,
You mean this one? Let me see.
right, this one, the
This one.
recirculation.
That's a recirculation. Yeah.
And so that's a bad idea.
Well, it
Because
is.
that's the one that made the air quality in the.
Yeah, that's right. Because if it's a bad idea if you don't make up for that fresh air. So if you speed up the ventilation, so if it's 10 or 15 below, it starts recirculating for 20 minutes, and then it goes on fresh air for 10 minutes, for example, and then it goes to recirc for another 20 minutes.
Okay.
So if that 10 minutes, when it's bringing fresh air to your house, it brings enough fresh air for that next 20 minutes, then it's all right. But it usually does not, because it runs on a speed. The speed of the fan is set in a way that if there is no recirculation, it brings you just enough air. So that's this picture. You see, if there is no recirculation, then you have about over 65 CFM per house with 4 people. So that's just enough. But once the recirculation starts, then you start reducing that airflow. So you would have to move these way to the right to have, say, 100, 120. So if the reduction comes in, you would still be at 60 CFM per minute in average over a course of 1 or 2 hours or so.
I realize if you reduce your flow, you're going to have a tendency to increase that CO2 level at night, right? But in terms of other pollutants, if you have a good filtration system on your ventilation system, then it's not quite as bad to not have as much ventilation coming in during those times because you're filtering it.
That's
Would
right,
that
but-
be correct?
But filters, they will mostly filter the mechanical particles. I mean, the VOCs and
Large particles too, they're not very efficient.
yeah.
So
It's foam.
And it costs you more money to drive it.
And if you use like very efficient filters like HEPA or ULPA filters, then the pressure loss of that filter will be so high that you will need much more electricity to overcome that pressure loss. So I wouldn't say that you should just filtrate the inside air and say that that's okay. You always have to have a fresh air, and it has to come in a right.
I think it kind of sounded, we feel that research is okay if you have a healthy home. However, if you have anybody who's compromised in your home, the problem with the research is it's not random throughout the day, but it comes throughout the day. So let's say you're washing laundry, you're doing a hot water wash and you're using chlorine bleach in that hot water wash. You're vaporizing basically chlorine bleach into your house, and all of a sudden it goes into research. So if you have compromised breathing issues anywhere in your house, they've just been loaded up with different chemicals or whatever. Or if you have any sort of outgassing that goes on in your house, the potential for that timing just to be at that point at some time in your lifetime is problematic. So that gets to be a challenge with the research function. And it's endemic to all of us as manufacturers. I mean, we're all trying to figure out how to get around that, believe me.
Another complication that I've run into with that recert function is that I've seen a number of houses where they ventilate the crawl space with the HRV system. Well, then when it goes into recert, you're living in your crawl space. You're bringing that crawl space air up to the house. And that's, I see that fairly commonly.
Not exactly a clean space usually.
Not always, no.
So something that's fairly common in commercial would be to use the boiler to preheat the air, incoming air in a ventilation system. So that's not done at all in residential. I mean, they've got a ground loop, but there's no provision in that German one for a loop that you could have a heating coil
Well,
zone from the boiler.
well, that's
It's a cost function.
you asked too early, but there actually is, and in Europe it is a common solution. In countries where you have a district heating, for example, so the costs of the heat are not so high and are much lower actually than cost of the electricity. So it's much more beneficial for you to use the hot water to preheat your air. The tricky part in that is that if the air is so cold, then the water cannot be just plain water because it would freeze again. So you need to have a small heat exchanger, and if it's a district heating, then you have to have a small heat exchanger and a small separate glycol loop with a pump, with an expansion vessel and safety valve and so on. That will run that. But it is possible, and it is done. And actually, the next producer, which is new in Alaska too, as I have heard, and we're gonna see their unit upstairs in a minute. They actually have that in their units. So but it's not a preheating, but it's the afterheating. So you have a flat plate heat exchanger HRV with a bypass with a hydraulic afterheater. So the fresh air comes in, goes through the heat exchanger, and then hits the afterheating coil, and then goes to the room. And you set the temperature outside the unit you want to obtain. So if there is a bypass activated, and if 90% of that cold air hits the heat exchanger, then there just will be more heating in that coil. If the fresh air goes bypass the heat exchanger and goes to the coil will just afterheat it. So you will always feel warm enough air in your house.
Yeah, as a home builder, the two most common reactions from having an HRV is the customer that says, my life is better because I have it, it helped my asthma, it helped my allergies. And the customer says, yeah, I don't use it, it uses energy, I don't want to waste, they have to plug it, they don't. So those are the two.
Blows
Yeah.
cold air and lock everything.
Right. Yeah.
But then
But
how much? Of course, once you have it, why not to use it? I mean, the running costs are not that high.
Well, you had a chart about that, but I think that is a piece of information that really needs to get out, because I literally know dozens of people who don't use their HRV because they think it's gonna cost them a lot of money. And $3 a month or whatever.
Well, the thing is, because, I mean, in a way, it's also a tricky chart, because people often ask, how much will HRV save me? Nothing, because if you haven't had it, you probably underventilated your house. Once you install it, you ventilate much more, so your heat loss is much higher. So you will actually pay more than you did before. The question is your indoor climate better, and do you appreciate that?
Your point is exactly right. I've seen this again and again. I think people in this room are on board with this. But I mean, I've got over 45 places that I put these in. And anecdotally, I know from 4 or 5 of them that the owners have turned them off. One, they haven't been trained. They don't understand, oh, it just freezes up, so I turn it off. And then they get frustrated and they look at their energy bills and say, well, I'm not saving as much, so I just turn it off. And these are not ignorant people. I know a person who's a pharmacist. And so one of the things that we have to stress as builders, architects, designers is we need to commission and train the users. We need to follow up. We need to come back year on year. Oh, you got this problem? Oh, here's a solution. But, you know, I walked away from some of these things for 20 years and I go back and I find 2 owners later, nobody's turned it on because it doesn't work. So it's an education and commissioning issue for the user. It's very important.
That's right, but it also has to be, systems need to be designed and installed as properly as possible.
Right.
Because if they bother the people, they will always find a way how to turn them on or how to compromise with them. Ilya, you had a question a long time ago.
Well, I guess the way I see it is that with the Vinmars and the light press that are on the market now, when we get 20 below or colder, they just start reverting into defrost, and so the air quality, when you need it most, you have it the least. Is that a correct assumption? I mean, because they're a simple system, they're not doing any kind of a bypass and just bringing in cold air, because the occupants would complain and that would hurt sales. So after say -20, I'm just sort of arbitrarily picking that temperature. Typically, those things aren't ventilating much at all. Right?
Yeah, it is unfortunate, but it is right. I mean, we don't use them in Europe, so I don't have so much experience with them. But when I was here 2 years back, that was the impression I got, that they just 20 below, and that's their limit.
Okay.
And now I mean, of course, it's gonna cost energy always. No matter how good your ventilation unit is, it's physics. I mean, you will have to somehow cover for that de-icing. One way or the other. It could be done better way or worse way, but we have to agree and we have to stress that the fresh air cannot be shut off. I mean, we just have to accept that it's going to cost some energy or money. So this is the third slide with the ventilation unit, and I say it's made in Scandinavia. Well, some of them are made in Sweden, some of them are made in Finland. The small ones are from Finland, and the big one we're going to see tonight is from Sweden. It's a huge company which owns about 80% of the North or West European market, so they bought lots of small companies. And this unit you can choose when you buy them whether you want a rotary or counterflow heat exchanger. They allow for demand control. They have a port for CO2 sensor, humidity sensor, humidistat from the bathroom. They have a Modbus connectivity, which is something never seen before in such small units, because it's rather expensive feature, and it's just because they have figured out how to do it cheap, or I don't know. It's just they have it. It's not really useful though, unless you are a geek who wants to have your unit hooked up to a control system. They have different defrosting strategies depending on whether it's rotary or counterflow heat exchanger. The rotary ones have electric preheating. It could be a water preheating as well. Then they have a flow reduction, and then they can reduce the rotor speed. They never compromise the fresh air supply. There's always enough fresh air coming in. And it goes like, first it starts preheating. If that doesn't help, I think there is a rotor speed reduction, and if that doesn't help, there is a flow reduction on the supply fan.
But in no case does it shut it off.
No, it's
And-
we're talking about several percent reduction, and then eventually the rotor would stop, and then you can have a full speed. But they still the control mechanism tries to find the right balance between the energy recovery and the fresh air supply. They have a fifth port, which is something useful, I think, as well. So they have 4 connections for return, exhaust, fresh air intake, and fresh air supply. And they have a fifth port for a range hood connection, which goes bypass the heat exchanger. It's just using the internal fan. So you can have your range hood without a ventilator, so it's not noisy, and you have it connected to the unit if you want to. I would especially recommend that for someone who cooks for a long time. If you cook for a couple of minutes a day, it doesn't make so much sense. You can just have your range hood connected directly to outside. But if you connect it to this and you turn the range hood on, then there is more exhaust through the range hood and less exhaust through the other ports in the house. So you all the time have a balanced ventilation. So the amount of air in equals the amount of air out. It also has a fireplace function, so if you are turning on the fireplace, it will overpressure your house. So in that case, it will actually reduce the exhaust, and it will pull more air in, so you don't get any smoke or any fumes from the fire sucked into the house through the chimney. And since it's a rotary heat exchanger, it allows for a moisture recovery as well. Well, besides ventilation units, which are of course very heart of the ventilation system, we also have air terminals. And they are somehow also a cause of trouble, because if they are chosen improperly, they might cause some noise issues or some draft issues. So it's very important to choose the right terminals, especially when we're placing the supply in a bedroom. That needs to be silent, and it needs to be flowing the air in a good direction, so it doesn't blow on the sleeping people. And of course, they can be as simple as this one, which I would only recommend for exhaust, and as complicated as these ones, which are more for the industrial application and huge airflows. We had a good experience with these, which have the face here, so the air doesn't go directly from it, and they have little flaps in here, so you can select which of the 4 directions the air will come. Plus, you can adjust the gap in the between the plate and the face here. Very important are the intakes on the facade. We have seen lots of these pictures where when there is especially when it's so cold and the snow is so light and you have a improper intake, then lots of the snow can get transported to the ventilation unit, and then eventually it can block the whole unit. So the intakes have to be protected, and also can have some nets to avoid the insects to enter, and it's important to put them as far apart as possible, because otherwise there is a risk for short circuiting. So the exhaust air would be taken in again. Ductwork, a big issue. Again, if designed improperly, there could be lots of noise problems. If using circular ducts like these, it is always important to think about the noise spread. Like if you have several bedrooms and they are connected one to each other through the ductwork, there is a risk that the kids or the parents will hear each other. It might not be such a big problem though, but yeah, it's good to think about it. Pressure loss when designing I've noticed that these are used very, very often in here. It is a good thing when you need to like connect something which is not really connectable with the hard ductwork, but otherwise I wouldn't recommend them because the inner face is so rough that you get so much dust deposits in it, and it's almost impossible to clean them, so you would have to replace them every second or third year. So I would definitely just use these as little as possible. Rectangular ducts, also a big problem to clean and big problem to make actually. What we have done recently is a system with this system. We install ventilation with these, and they are very, very comfortable. You have it's similar to floor heating basically. You have your ventilation unit and it's connected to the distribution box like this. Then you go to each room. You go with a single or double line of this tiny pipe. The internal, you can bend it, but the internal face or the internal surface is completely smooth, so there is very little dust deposits in it, and it's very easy to clean because it goes with no turns or with no branches from this box in a mechanical room all the way to the terminal in the room or in the bedroom. So these have been very, and especially for renovations, for example, if you need to go somewhere or you have a very little space, so the big duct would be difficult to hide, these have really been a success. This is how it could look. You have the ventilation unit, then through silencers you connect two distribution boxes, and then from each box you go supply and return two different rooms. Filters, as we have talked about, again, they could be more or less efficient. The good thing is that usually the ventilation unit, they don't come with very, very advanced filters. They only have the very, very basic filters to filter out dust, to protect the unit itself, to protect the fans and to protect the heat exchanger. But if you want something better, you can change those filters, or you can install extra filter box. We're gonna see that in our tour as well. And then you can use standard made filters, which could be either high efficiency or ultra low penetration filters. If you have some smell issues from the outside environment, you can use carbon filters, or in kitchens, of course, fat filters as well. So a study we've done recently up in Sisimiut was a renovation of a house in here. It is a row house, a single family, and when we came in, there was only a range hood with an active fan and two exhausts, which were just natural shafts from the first floor and from the second floor, from the bathroom and laundry. And then there were 3 fresh air inlets on the wall. What we did, we installed a ventilation unit from Sweden in the laundry, and then with the 2 distribution boxes, and we used the shafts, the natural shafts, which were originally for the natural ventilation, to pull the tiny ducts up and connect to one bedroom and then to the other bedroom, and then we had an exhaust from the bathroom as well, an exhaust from the kitchen and from the laundry itself. The ventilation unit came with a controller, which we preset in a way that the users can never turn the ventilation completely off. They can go to a mode which is away, which would still deliver some air, which would be silent, which would be no draft problems, no nothing, but still there will be some air change. And then, of course, when they are home, they could go to a home mode, which would deliver the required air change. Or if they have a party or something, they could go to a boost mode, where it boosts up and exchanges the air much more than normally. These 3 options are the only options the tenants had. And the unit was wired through the wall, so they couldn't turn it off. And we kindly asked them to just bury with that for 3 weeks or 4 weeks until we do an interview with them and see if they hate it, we adjust it, or if they like it, we just leave it as it is. There was a hydrostat in the bathroom where they can set the relative humidity at which the unit goes to a boost mode. So if in the bathroom they take a shower, the hydrostat will sense it and will just kick in the boost mode immediately. This is how the ductwork looked. It's a little messy, I know, but given the space, it's taken with a wide eye lens, so it looks like a lot of space, but it actually wasn't. So this is the shaft to the upstairs. Then we went down and underneath the staircase. It's really good with these because they can bend and you can really go to tiny places. And then then just the flexible connections are
And
short.
the insides of those are nice and smooth, right?
Yes, on the inside is completely nice, and these green ones, they actually have an antibacterial layer in them. That's what the producer says.
4-inch diameter?
No,
approximately?
it's let me see, 60 millimeters. That's
16?
like that's 1.5 inch. No.
Did you say
10 inch.
16 millimeters?
2.5.
2.5. Yes, 6 centimeters. Yeah, 2.5 inch. Yeah.
And they all stay inside the envelope, right?
Say it again.
All of these are staying inside the envelope.
Yeah, they are all in, so they are not insulated because they are in a heated space. That's a rule. You never put your ductwork into the unheated space. That would be a mistake. Of course, these need to be insulated because they go to the inside, to the outside, and then these two are insulated too because of the noise the dumping. And if you need to bend these more than possible, then you can get the metal bends. But still, with a cleaning brush, you can easily. We have a brush which is on a long wire, and you can just pull it through the duct all the way, and clean it that way. So what happened with the indoor environment? We have 2 nights here as well. This is the chart which was shown on one of the first slides, and then after we installed the ventilation unit, the nights look like this. We are still a little bit above the 1000 or 1100 ppm, but we are very close to that, and the second night here also is below 2000 at least. And you see the ventilation kick in, and now we are at 700 ppm in here. So the ventilation, the indoor air quality improved a lot, and it was not only measured, but it was confirmed by the people. It's a family of 5 people living there. No, it's 7. It's 5 kids and 2 parents in such a small. It's a 600 square feet apartment, and they were.
No dogs, cats, or anything?
It's European standards, you know, so we used to live small, but not that small, I must say. So they were really happy about that, and the mother said that even the kids got to realize that there is something happening in the house, that they feel somewhat better. Also the humidity, that was a good finding actually, because before, the humidity was not an issue before either. It was below 50% for all the time when we measured. But we were curious to see how it changes when we install the ventilation. We expected that it's going to drop a lot, but actually it did not. For most of the time, for 77% of the time, it actually stayed within the 30 to 50% range. It actually was more than before because the lower end got higher, and we think that's due to the moisture recovery ability of the wheel, that some of that moisture from here shifted a little bit up, so that actually couldn't be better. What we've measured in the bathroom, that was somewhat expected, because before there was just a natural shaft, so when somebody took a shower, and the humidity raised above 50, it took, let me see, 2 hours for the humidity to drop back to the safe region. Whereas after the installation, when the humidity got above 70, I think, or about close to 80, then the booster kicked in, and then it was just a matter of minutes to bring that humidity back down to a safe zone, which is a huge mold prevention, especially in the bathroom. So what did we find? The indoor air quality was improved not only by measurement. We not only measured that, but also the inhabitants experienced that. They haven't complained about anything. The only complaint was noise. When they went to the home mode, they were complaining that in the nighttime it's a little noisy. If the house gets quiet, they could hear the air. So we installed a little silencer on the ducts leading to the bedroom, and we lowered the speed a little bit by 2%, I think, and that or 5%, and that helped a lot. So when we visited them next time, they didn't complain at all. It was done at reasonable costs, given the return of investment, roughly about 14 years. But more than that, mold prevention is a huge money saver, because to mitigate a mold problem in such a remote area, it's insanely expensive. And of course, it improved the comfort, which is the most valuable thing. So in general, to conclude with, we know that there is something with the ventilation in the Arctic dwellings. It's poor, and even new dwellings have problems, and we should focus on that, and we should do something with it. And we try to. Natural ventilation is not an option at these latitudes. Mechanical ventilation proved to work. There are some limitations to it due to physics and due to some missing development, but we are heading the right direction, I can see. Frost and snow issues always need to be addressed. It hasn't been like that always up in Greenland, and that's why ventilation hasn't got a very best name. And therefore, it is very important to design properly and to control the ventilation properly, so it doesn't, so some of the problems are avoided. And it is very beneficial to have a moisture recovery for the relative humidity management. So yes, it is a harsh place to live in, but there is something what makes people happy in the air. We just need to bring that air inside. And thank you for your attention.